Hi everyone, welcome to part 2 on our video lecture on section 3.1 dealing with the introduction to the derivative. In the previous recording, we saw that the derivative was nothing more than the slope of the tangent line or the instantaneous rate of change. In this video, we're going to be taking a look at more examples and applications of the derivative. So let's go ahead and begin with this problem. Let's see if we can find the equation to the tangent line of the function f of x equals to the square root of x at x equals to 2. Alright, so if we're looking for the equation for the tangent line, at some point we will need to know what's the slope of this line. Now the slope of the tangent line, as we just said, is the derivative at some value for x, which I'll call this one here a for now. And don't forget, this is the slope of the tangent line, which will be equals to the limit as h approaches 0 for f of a plus h minus f of a all over h. Alright, so using our function and putting it into the definition of the derivative, we're going to be getting the limit as h approaches 0 for the square root of a plus h minus the square root of a all over h. Now, if we go ahead and evaluate the limit using direct substitution, then we would get the indeterminate form 0 over 0. But by now, hopefully you practice enough problems involving radicals to know that if you wanted to simplify this limit, we would actually need to go ahead and multiply by the conjugate of the numerator. So we're going to go ahead and multiply here by the square root of a plus h plus the square root of a, both top and bottom. Alright, so let's go ahead and continue simplifying here. So the nice thing about multiplying by conjugates is that you can just go ahead and use a shortcut and really just multiply the first and the last. And don't forget, the denominators, I don't want you to distribute them. I want you to keep them as a product. Alright, so let's see. What do we get on the numerator? We're going to get here the derivative at a is equals to the limit as h goes to 0 for a plus h minus a all over h times the square root of a plus h plus the square root of a. Now good news here, we do get to see here that the a's on the numerator cancel. So that means that we're just left with an h on the top. But I'm also multiplying by an h on the bottom here. So I can go ahead and cancel the h's as well. Now careful here though, because the cancellation of a minus a was equals to 0, but h divided by h was equals to 1. So that means that we're left with the limit as h approaches 0 for 1 over the square root of a plus h plus the square root of a. Now as the h goes to 0, this is gone. So we're just going to be left with a 1 over the square root of a plus the square root of a, which gives us a 1 over 2 times the square root of a. And there we go. Our derivative evaluated at a, any a, is equals to 1 over 2 times the square root of a. And this is telling us the slope of the tangent line at any a that we want. Okay, now this particular problem is asking us to find the slope of the tangent line at x equals to 2. So at x, which is the same thing as the a equals to 2, let's see what will be our derivative. Well, f prime evaluated at 2 is equals to 1 over 2 times the square root of 2. Okay, so now that we got the slope of the tangent line, what is the actual equation for the line? Alright, so let's go ahead and see. Remember that the equation for a line, or in this case the tangent line, is f of x minus f of x of 1 is equals to the slope at x1 times x minus x1. And again, guys, I would prefer for you guys to remember this formula, but if you want to keep on using other forms, that's perfectly fine with me. Now, notice that we have almost everything that we need to complete the equation for the tangent line. We already know the slope, we already know the x value, but what we don't know is, hey, what is the y value that's associated with our input of 2? So let's see. What is f of 2? Because again, this is basically the same thing as, well, I'll leave it here. F of 2 is equals to the square root of 2. All right, so putting everything together then, the equation for the tangent line is f of x is equals to, well, I guess I'll include the subtraction here. F of x minus the square root of 2 is equals to 1 over 2 square root of 2 times x minus 2. And there we go. We got the equation for the tangent line here. Again, this is fully simplified. I don't want you to do any additional work, but if you wanted to go ahead and add the square root of 2 to both sides, that's perfectly fine here. And this is another form of the answer. All right, now, because I want you to see what is going on here, are we really finding the equation for the tangent line? Let me go ahead and show you how the function, the square root of x, looks like, and did we really get the equation for the tangent line at x equals to 2? Okay, so here we have the graph of the square root of x, and I have labeled here the point 2, comma, square root of 2. All right, so what we're trying to do here is find the equation for the line that is tangent at this point. So in other words, a line that is only touching the curve at this point. Well, I'm going to go ahead and display the equation that we got here. The 1 over 2 times the square root of 2 times x minus 2 plus the square root of 2. And lo and behold, we indeed get a tangent line exactly at x equals to 2 here. And that's what we're looking for. The slope when x is 2, the slope of the curve when x is 2 is 1 over 2 rad 2. And here we have the equation. So we're representing here the instantaneous rate of change at this point here. Okay, now let's go back to our notes. The next example here is a nice application of the derivative. Since we already discussed that the derivative was the instantaneous rate of change, well, now we can use the derivative to find out what is the instantaneous velocity for an object. So let's go ahead and begin with example 3. Let's see if we can go ahead and determine the instantaneous velocity of a car at t equals to 3, whose position is given by the following function, s of t equals to t squared plus 2t. All right, now, I want you to remember that when we were discussing the concept of velocity here, we were talking about a rate of change. We're talking about the rate of change of how fast the position was moving. So velocity here is a rate of change. So in this problem, it's mentioning the instantaneous velocity. In other words, the instantaneous rate of change. Well then, we're looking for the slope of the tangent line. So it is s prime at a. So we have to use our trusty formula here. S prime at a is equals to the limit as h approaches 0 for s of a plus h minus s of a all over h. Now for this problem, guys, again, remember the s function is given here, but this problem, I do want you to try it on your own. So once you work on this one, you can go ahead and submit your completed work once you turn in the notes. Now, not to leave you hanging, I'll give you the answer for this one, and notice for this one, I'm not asking you to find out what is the equation for the tangent line. No, I just wanted you to tell me what is the instantaneous rate of change at t equals to 3. So the answer that you should be getting here, s prime evaluated at 3, you should be receiving an 8. So again, you try and verify the answer. Okay, perfect. Now, I want to go ahead and take a look at one more application problem. And this one here, I don't know. I find it a little bit more interesting than the previous one. Let's take a look at this problem then. So we have then the sound intensity, I, measured in watts per meter squared at a point x meters from a sound source with an acoustic power P, is given by the following function. I of x is equals to P over 4 pi x squared. Now, a typical sound system at a rock concert produces an acoustic power of about 3 watts here. What we want to do then is figure out what is I prime of 3 and interpret the result. Okay, so let's go ahead and take a look at this one here. So we are given the function I of x is equals to P, but for this particular problem though, we do know that P is 3. So we're going to have here 3 over 4 pi x squared. All right, now we're looking for I prime of x, which is equals to the limit as h approaches 0 for I of x plus h minus I of x all over h, which gives us the following: the limit as h approaches 0 for 3 over 4 pi times x plus h squared minus 3 over 4 pi x squared, and it is all over h. Oof. All right, so how can we simplify this one here, guys? Now for this one, I want you to notice something. Notice that both of the fractions have a 3 over 4 pi. So what I'm going to do here is I'm going to go ahead and factor out a 3 over 4 pi from the numerator and then take the limit, because the 3 over 4 pi is just a constant. So I can move it outside the limit if I want. It's some of the limit properties that we've discussed. So once we factor out the 3 over 4 pi, we're left with this. Now notice that we're taking the limit as h goes to 0, but now that we've taken out the 3 over 4 pi, I do believe that the simplification here seems easier. Alright, now at this point, it's completely up to you how you want to proceed, but I'm going to go ahead and rewrite the numerator in terms of a single fraction. So I'm going to go ahead and look for the LCD here, which is an x squared times an x plus h squared. Alright, so it looks like the first fraction is missing the x squared, and the second fraction is missing the x plus h squared. Okay, so simplifying this further, let's see what we get, which should give us now this complex fraction, where on the numerator, I went ahead and multiplied by whatever was missing for each fraction, and don't forget to FOIL out the x plus h squared. Alright, now to continue simplifying it here, I'm going to go ahead and distribute the negative, and might as well just go ahead and get rid of the complex fraction by multiplying by the reciprocal of the denominator here. And this should get rid of the h in the denominator here. So no more complex fractions. Alright, so let's see, what else can we get here after simplifying? Alright, so we're going to get then that I prime of x is equals to 3 over 4 pi times the limit as h approaches 0 for x squared minus 2hx minus h squared all over h times x plus h squared. And now we can see that some of the canceling happens. I can cancel the x squareds here. Now I also can cancel one of the h's, and it looks like we are now left with 3 over 4 pi times the limit as h goes to 0 of negative 2x minus h all over x squared times x plus h. Now we've done as much simplification as we can. Now it's time to evaluate the limit. Alright, so as h goes to 0, this is gone. This one here is gone. So it looks like I prime of x is equals to 3 over 4 pi times negative 2x over x cubed. Oh, actually not cubed. My mistake. This one here was being squared. So this is actually now, well, x squared times x squared is going to be an x to the fourth. Now, at this point, yes, we found out what is the derivative, but I do believe that we can simplify it a little bit more. So I see a 4 on the numerator, on the denominator, and a 2 on the top. So I can go ahead and simplify the 2 fourths here, which is going to give me a 2. And then I can cancel one of the x's here with one of the x's here. And this should now give us our final answer. We're going to have a 3 negative over 2 pi x cubed. There we go. Now we cannot simplify further. Now we have found what is the derivative at any x. In other words, what would be the slope of the tangent line for the original function at any x. Alright, so last and final thing to do here, or second to last, now that we know what is the derivative, what would be the derivative evaluated at an x value, which was measuring the distance away from the sound source, x meters away. Now for our problem is 3. So what would be the intensity of the sound? Well, not quite the intensity, but the rate of change of the intensity of the sound at 3 meters. So I prime of 3 is going to be equals to a negative 3 over 2 pi times 3 cubed. Now at this point here, rather than cubing the 3, I'll recognize the fact that I have a 3 on the top, but I happen to have 3 3s on the bottom. So I'm going to go ahead and cancel one of them here. And we should be left with a negative 1 over, well, 3 squared is 9 times 2 is 18 pi. Ta-da! Now we know the derivative when x is 3. Now this problem was also asking us to interpret the result. So what is this negative 1 over 18 pi telling us? Well, because the derivative, again, it is a rate of change, what we found out right now is the instantaneous rate of change for the intensity of sound when x is 3 meters, or when you're 3 meters away from the sound source. So let's go ahead and put this one here in words. So the intensity here is, now since it's a negative here, and it's a negative rate of change, so we'll say that the intensity is decreasing at a rate of 1 over 18 pi. Now what were the units? Well, remember that the intensity was measured in watts per meters squared, but because it was a rate of change, depending on how far away you were from the source, then it's 1 over 18 pi watts per meter squared per meter. So the farther away that you are, and that makes sense, then the intensity is going to be decreasing. If you've been to a concert, if you're really close to the sound source, really loud, the farther away that you get away from the sound source, yeah, it's not as loud anymore. Okay, so we have here that the intensity is decreasing at a rate of 1 over 18 pi watts per meter squared per meter when the distance from the sound source is 3 meters. And there we go. Now this one here was a little bit more of a doozy, but I think it was a good problem overall. Alright, so this concludes our video recording for section 3.1, dealing with the introduction of the derivative. We'll continue on with the rest of the topics on Thursday. See you then.